All right, here are the last two videos. We're getting so close to the end of the beast chapter of second semester. This Ksp Solubility Product can be used to predict if a precipitate will occur. Qualitative Analysis actually is your lab practical after the AP test. It's just a way of looking for ions in solution and trying to make precipitates of ions in solution. It is like pretty qualitative in that we're just kind of looking for what's present, what's not present. Will a precipitate form, yes or no? So we're going to use that Q. Remember your friend Q, the reaction quotient? We were using that before, like to predict if something was at equilibrium or not. We were comparing Q to K, and if Q was too big, we would shift one way or another. We can kind of do something real similar here. Sometimes they'll call this an ion product, which I think I mentioned earlier. When you look at Ksp equilibrium expressions, maybe we have this calcium fluoride. So we might have something that kind of looks like calcium fluoride. And we're looking at its tendency to dissociate or dissolve in solution. Would we form calcium ions and fluorine ions? Ooh, I should put 2 fluorine ions. There. 2 fluorine ions in solution. There, I like that better. So, when we were setting up our equilibrium expressions with solubility, we kind of said that you don't use the pure solid, so it really is just a product of the ions. If we go products over reactants, we're not using the reactants. So the term ion product kind of makes sense. We're looking at a product of the ion concentrations. When you do Q, it's going to be the exact same setup as K. So, I would have something that kind of looks like this if I was doing my K or Q. I'd have the concentration of calcium ions raised to the first power, and I'd have the total concentration of fluorine raised to the second power. I would raise it to that coefficient in the balanced equation. With Q, just as before, we use initial conditions, not necessarily equilibrium conditions. So they may give you a set of conditions, and we would use that as initial. They're trying to show like I down in here. I equals initial. And from that Q value, we can kind of predict if a precipitate will occur. In general, I kind of do just follow these guidelines. If Q is too big, in other words, your ion product is too big. It's bigger than K. There must be too many ions in solution. Well, if there's too many ions, how are you going to solve that? You're going to form a precipitate. So if Q is greater than K, again, that kind of means your ion product concentrations are too high. I want to bring it back to equilibrium, so I'm going to shift this thing toward the solid. That should reduce the ion concentrations. If Q is too small, then no precipitate will be formed. And that's really all we're looking for. We're not necessarily talking about it shifting forward or reverse. They're going to say, will this form a precipitate, yes or no? So again, like if my Q is too small, then, to make it bigger, I'm going to form more ions. So I won't see any precipitation. It could look something like this if we put numerical values to it. This is a weird compound. We don't have any cerium iodate, but I guess we can play along. I've got a solution containing 750 milliliters of a 4 times 10 to the negative third molar cerium nitrate solution. We're going to add 300 milliliters of 2 times 10 to the negative second molar potassium iodate. We want to know if a precipitate will occur. Okay, I'm going to suggest one thing. Kind of like titrations. When you join solutions, you're combining volumes, and that's going to kind of affect your overall molarity. So I would recalculate the molarities first, just like what we did when we had the titration problems. So let's say we look at the cerium nitrate, and O3 M1V1. The original molarity, let's I guess we can use it. 4 times 10 to the negative third molar. The original volume is 750 milliliters. Let's calculate the new molarity when we join these volumes. So we're adding 300 milliliters of the other solution. So I'll have a total volume of 1,050 milliliters. It's totally fine to leave these in milliliters. As long as both volumes are in milliliters, that's fine. So let's do this molarity. 0.00286 M2. 0.00286 molar. Now, the precipitate we're looking for is this cerium iodate. So of the cerium and the nitrate, the only ion that I really care about is the cerium. And for each mole of cerium nitrate, I'll get 1 mole of cerium ions. So we could say that this is like the molarity of the cerium, and it must be +3. The nitrate's going to be a spectator. Nitrate is soluble with everything. Now we do the same thing with the other reactant. It was potassium iodate. So the original molarity is 2 times 10 to the negative second molar. Whoa, boy. You could take these out of scientific notation, too, if that bothered you. There's 300 milliliters. We want to know the new molarity at a little over a liter. 1,050 milliliters. M2. How about 0.00571? And now kind of similar, of these two ions, the potassium and the iodate, potassium's aqueous with everything, so I'm really only concerned with the iodate ion. So I could just kind of label this as iodate. All right, so again, I would suggest doing that right away, just like a titration. You got to do it at some point because we are going to change the molarity as we join volumes. Now, you can write these reactions in either direction. Technically, I'm combining the solutions and I want to know if this precipitate forms. So I might kind of write this reaction as the cerium +3 ion. And again, they kind of like tell me the formula. I would need 3 iodate ions. And then I want to know, like, what's this tendency to form a precipitate? The cerium iodate. IO3, 3. And if you wanted to, you could put phase symbols in. Everything on this reactant side is aqueous. These are ions. And this would be my precipitate, if it forms. All right. So you've got your new molarities. You can set up an ice table if you want to, but you don't necessarily have to. We can kind of set up the Q calculation right away. Q equals a product of the ion. So I'm not really thinking about this as product over reactants. I'm not going to use that solid. So it really is like an ion product. So if I had the cerium, I want to use like that new cerium molarity, 0.00286 molar cerium ions. That's going to the first, times the iodate, which originally it's 0.00571 molar IO3. And I'm going to raise that to the third power. Now, sometimes people will be like, aren't you supposed to multiply that by 3? Not for Q. Q uses your initial molarities. This is what I have. I don't know if it's equilibrium. Yeah, at equilibrium, there should be 3 times as many iodate ions as cerium ions, but I don't know if we're at equilibrium. So that's kind of a common mistake. Sometimes people will think that they need to multiply that by 3 because of the ratio in the equation. Not for Q. We're going to plug this in, see what we get. Q equals, yucky, 5 0.32 times 10 to the negative 10. Holy cow. That's small. That's small, because if I look at K is given to me up in the original problem. It's like I guess they're both small. 1.9 times 10 to the negative 10th. I didn't even realize that. They're both tiny. But Q is larger than K. Let's see if we can get a little more room down here. Boop. There we go. Q is larger than K, which means that those ion concentrations are too large. So how do we bring Q to equal K? We need to reduce those ion concentrations, and the way we do that is by forming a precipitate. So really all they're asking me up on top is, will this precipitate form? And we would say yes. A precipitate forms. And if I had to justify, I would just say, well, because Q is larger than K. So to reduce Q, the ion product, I would need to form that precipitate. I need to reduce the concentration of those ions.